Okay, made a quick transition over here. Welcome back, everybody. So we're going to get started with this next session. This is talking about enabling technologies for the Moon to Mars Space Exploration Initiative. Our sponsors for this session are our full day sponsor, Northrop Grumman, as well as KBR and the University of Tennessee Space Institute. Our moderator is Jim Ryder of the Space Technology Mission Directorate at NASA. So Jim, take it away.
Yeah, thank you, Jim. And I want to welcome everyone to the Enabling Technologies for the Moon to Mars Space Exploration panel. As NASA embarks on its next era of exploration, advancing technologies and testing new capabilities at the Moon will be critical for crewed missions to Mars. The plan for a sustained lunar presence will require advances in technology and the development of innovative systems. Technology drives exploration to the Moon, Mars, and beyond. And this panel will discuss some of the key technologies NASA is developing to support science and human missions that will enable future exploration. And so it's my pleasure to introduce our four panel members. Niki Werkheiser is a leader for innovation and technology development as she serves as the program executive for the game-changing development program within NASA's Space Technology Mission Directorate. Niki also leads the Lunar Surface Innovation Initiative and is responsible for identifying and addressing key technologies needed for a sustained lunar presence. And Jason Ballard. Jason is a co-founder and CEO of ICON. ICON is the construction technologies company using 3D printing to advance humanity and is truly an excellent example of leading innovation in terrestrial applications while also supporting space applications that fill our technology gaps. Jason has dedicated his life to working on big problems at the intersection of human civilization and the natural world, and I'd consider that quite an epithet. Mike Seablom is Chief Technologist for NASA's Science Mission Directorate. He has the responsibility for surveying and assessing technology needs for heliophysics, astrophysics, earth science, and planetary science divisions, and is our primary liaison to NASA Office of Chief Technologist and Space Technology Mission Directorate. And Mike Kynard, the manager of NASA's Space Nuclear Propulsion Office at Marshall Space Flight Center. Mike manages the design and development of nuclear propulsion solutions to achieve reliable Mars transportation and other applications. So what I want to do is ask each of the panelists to give just 5 minutes of introductory comments, and then we'll go on to both questions that I have for you and especially from our audience. And so Niki, would you lead us off, please?
Hi there, everyone. Can you hear me okay? Good. Okay, good deal. Double checking. You never know these days. Hi there. I think we're going to pull up some charts. I'll give those just a second. I am thrilled to be on the panel today speaking about how we are enabling technologies, and we can go on to the next slide. As I often say, I'm Southern, but I'll speak quickly because I know we don't have a lot of time and I want to get to questions. So in space tech, our mantra is really technology drives exploration. Our programs are aligned along the technology readiness spectrum, all the way from low TRL in our early stage areas, which focuses heavily on R&D and engages primarily with universities across the nation. Then mid TRL, which is really the bridge from that R&D to commercial infusion. I'm going to be talking more about that today with the game-changing development program, as Jim noted. And then finally, the high TRL, which is really focused more on mission and or commercial infusion. So it works more with industry and engineering implementation into the NASA missions. I'm going to go to the next slide. So the game-changing development program, we really fall in the mid technology readiness level, as I mentioned. That's really our range of 3 to 6 or so primarily. Generally taking technologies from the initial lab concepts to a complete engineering development prototype. The most exciting thing to me about working in technology development, and actually particularly with this mid-TRL range, is that you truly do get to see the transformational technologies come to life in real time. Of course, not every technology works out, but when they do, it can be truly, well, game-changing, and that's why we do call it that. And not just in space, but right here on Earth as well. So if we can go to the next slide. I want to talk some about the Lunar Surface Innovation Initiative. It spans across the space tech programs and those TRLs that we talked about. with a high percentage falling in that mid-terral range currently. So LSI was created to really spur the development of those technologies needed for sustainable operations on the moon. Here you can see the 6 technology areas for LSII that we work to develop across industry, academia, nonprofits, and the government. So if you pull these threads a little, you have in situ resource utilization, or ISRU, which is really how are we going to use the resources on the moon to get consumables for the astronauts and propellants for our rockets. And then how can we use those same resources in conjunction with additive construction and excavation technologies to build structures like landing pads and possibly even habitats, as Jason will be talking more about. Of course, to do any of these things, you must have enough power generation and the ability to store energy. So we're developing fission surface power, regenerative fuel cells, solar arrays, and other novel technologies in that area. In order to do all of these things, you really have to be able to survive the extreme environments of the moon. We have to enable rovers and manipulators and other systems that can operate within the conditions of lunar noon, which is up to 150 degrees Celsius, lunar night down to minus 180 degrees Celsius, and even the permanently shadowed regions down to minus 240 degrees C. And then speaking of the rovers, you have to be able to access these areas. So in extreme access, we're developing small scouts and rovers to access areas that may really be too dangerous for humans, such as those permanently shadowed regions where we believe there's a lot of water and other resources. And even the things that may seem trivial at first, such as dealing with the dust on the moon, require new technologies. You'll notice here that we do call this dust mitigation and not dust solutions. And we're approaching that with active, passive, and operational technologies that we'll be employing. So you can really see how each of these capability areas are critical both individually as well as how they work together to develop an interdisciplinary ecosystem that we really need for truly sustainable missions. If we can go to the next slide. And lastly, I just want to say I'm very proud that within just a little over a year of establishing LSII, we have been able to engage over 232 organizations across 36 states to shape these technologies that are needed in order for sustainable lunar presence and to stimulate a lunar economy. This includes efforts across that technology spectrum, both in-house as well as a combination of competitive challenges and partnerships. We're really fortunate that we have so many amazing collaborative tools in our toolbox that we can employ in a multitude of ways. And that's one of the things I'm really most passionate about doing. Some of these that we've employed include crowdsourcing, such as our Centennial Challenges, tipping points, which we refer to because we consider these capabilities at a tipping point in their development because we believe NASA investment is that extra push they need to mature them for a mission or commercial infusion. Small Business Innovation Research Awards, NASA Innovative Advanced Concepts, multiple space grants, and more. And in order to really ensure that we are amplifying these opportunities and coordinating across the rich and diverse stakeholders to develop these capabilities, we established the Lunar Surface Innovation Consortium, which is led by the Johns Hopkins Applied Physics Labs. 2 weeks ago, we held the fall consortium meeting. We had over 400 participants with Administrator Reuter and Bridenstine, with over 160 organizations participating in the monthly focus groups as well that we've established. We have virtual monthly focus groups across the 6 LSI capability areas. Of note, I'd like to say that over 50% of those participants had not previously worked with NASA Space Tech, which is one of our goals, is to make sure that we are diversifying and have our traditional space, new space, as well as non-traditional NASA participants that are interested in developing these capabilities as well. So I would encourage anyone that's interested to check out the LSIC website there at the bottom of the chart, and I look forward to questions a little bit later on. Thanks so much.
Thanks, Nikki. Nice summary. Jason, would you want to take on now?
Yeah, happy to. I'll wait for the slides to come online. It's a real honor to be here today, and thanks for giving me a minute to do some table setting. Everyone knows what NASA is. ICON's kind of the new kid on the block. So next slide. So the big animating idea at ICON, given that shelter is a basic human need and construction is a very basic human activity, is that a paradigm shift in the way we do those things is a really big lever. And we want to use that lever for good. So advanced construction technologies that advance humanity is the order of business. Next slide. So toward that end, we work in fundamental research and development on robotics, software, and novel building materials that will enable that paradigm shift. Next slide. What you see here is that the first place we have put those technologies to work was in the service of trying to solve this global housing crisis. And here you can see our Vulcan 2 printer printing 6 houses at a time, or 6 in a row, printing 3 at a time, and all 6 in fact, having different floor plans. These houses were delivered for an organization in Austin, Texas, providing housing for people experiencing chronic homelessness in Austin, Texas. However, solving problems isn't the only thing you get to do with this technology. We also get to open up tremendous opportunities for humanity. Next slide, which I know we're all excited about here. Of course, to become a truly spacefaring civilization is one of the more exciting prospects for all of us. In 2018, the same year we printed our first house, we began participating with NASA in their 3D printed habitat Centennial challenges. That was our onboarding. We were an award winner and a finalist in that competition, and that opened the door for continuing relationship with NASA. Next slide. And so as we continue to study the problem, our conviction that 3D printing or additive construction was going to be a necessary tool in the belt of a spacefaring civilization only increased. We got more confident. From a financial perspective, we ran the numbers, and simply getting the dry materials to the lunar surface for a small house is going to be like on the order of $1.4 billion. That is not sustainable. And at those prices, it's going to be very hard for us to have a permanent presence on the moon or Mars. With 3D printing, we can learn to live off the land, use in situ resources, and give ourselves a chance to really do this. Next slide. And it's not habitats only that you need, of course, for a permanent presence on the moon or Mars. You need like a whole suite of infrastructure. And so once again, 3D printing allows the possibility of a single system that delivers multiple infrastructure elements instead of a lot of specialized systems with their own development costs, transportation costs, and support costs. So in short, I mean, we really think there's some there, and NASA seems to be building similar conviction. Next slide. And so, as some of you have heard, NASA recently joined a SBIR with ICON, the Air Force, and the Department of Defense to begin development of an off-world construction system that we call Olympus, in a way that we all share costs and risks, which is, super cool. So we've kind of gone from Centennial Challenge now into the SBIR phase. We begin working very closely with the Marshall Space Flight Center and 2 architecture firms, Big and Search, to establish kind of provisional high-level requirements that have allowed us to begin high-level system concepts that you can see here. Next slide. Also, we've begun benchtop testing of deposition systems that will actually enable additive construction on the moon. Concrete's not really an option with the whole triple point of water thing. We're testing microwaves, lasers, infrared, kind of the whole electromagnetic spectrum minus X-ray and gamma rays, but to establish baselines and to down select and refine design to get ready to really do this. Next slide. So the Olympus system design is really underway, and we continue to believe that this approach is directionally correct. Next slide. And just to carry the imagination a bit further, here you see launch and landing pad infrastructure highlighted with one of the Olympuses coming down on a lander and another hard at work in the background. Next slide. And here you see an overhead of both roadways and dust mitigation pads and an overhead habitat delivery involving kind of a mixture of actual printing and dry regolith placement for insulation shielding to increase the speed of delivery and to decrease the cost of both power and money. And it's I'm biased, but I think this picture is really cool. It kind of, this is all sort of not as science fiction as it may in fact look. Our confidence is going up. So next slide. It is still early days, but we have not encountered any law of physics reason that this won't work. And we're hoping to have ICON hardware on the moon in this decade. And ultimately, next slide, on Mars as well. And we think we've experienced this journey from like early stage Centennial Challenge into SBIR level, kind of mid-level development. And we're hoping to get to continue the journey with NASA and other partners. Thanks for having me.
Thanks so much, Jason. That was fascinating. I look forward to hearing some more. Next, we'll turn to Mike Seablom.
Okay, thanks, Jim. I just have a couple of charts. If we could get those up. Okay, great. And let's see. Good. Okay. So I'm Mike Seablom. I'm the Chief Technologist for SMD. And we could go to the next chart. Just wanted to talk a little bit about the support we're providing for Artemis. As you know, in our planetary science division, we've had lunar science requirements for some time. These key science drivers have not really changed since the advent of the Moon to Mars initiative, but we are now promoting them, and we're focusing on them more than we were before. The key science drivers for SMD, for lunar exploration, include studying planetary processes, understanding the volatile cycles, looking at even outgassing and from the lunar surface, discovering the history of the Earth-Moon system, which is a complete record of it on the surface, record of the ancient sun, studying the universe from a unique platform. This could include radio astronomy from the dark side of the moon, or other unique capabilities for science. And then just unique science from the lunar environment itself. Okay, next chart. Okay, so in our mission directorate, we have three key science themes. We want to discover the secrets of the universe, search for life elsewhere, and improve life on Earth. Sustained investment is critical to our success. Our approach is to mature the enabling technologies years in advance of science mission implementation, so that we retire risk, reduce cost, and grow capabilities. Implementation is performed through our four primary research divisions, which are astrophysics, planetary science, heliophysics, and earth science. And the National Academy's decadal surveys, which I've shown on the lower left, these are the foundational documents that we use to identify our science goals. Our technology investments within SMD are primarily focused on science instruments. They totaled to over $500 million across the Directorate per year, and more than a dozen programs that I've shown here on the right. I mentioned all of the divisions and all of the programs because in many instances, the technologies are cross-cutting. The science instruments that we're developing for heliophysics and for Earth and astrophysics, we can certainly use for the moon as well in many cases. I've circled two of the programs that were added specifically to support the new lunar initiative. These are the development of advanced lunar instruments, the DALI program, and the Lunar Surface Instrument and Technology Payloads, the LSITP program. In DALI, we recently made selections in areas such as advanced spectrometers for detection of water vapor and other lunar volatiles, a drill that will penetrate up to 3 meters in depth to detect the moon's thermal properties, sample acquisition and analysis technologies for lunar regolith. In LSITP, we selected a fast-moving rover, a wide-angle imager, radiation-tolerant processor, a magnetometer, a number of other science instruments and acquisition technologies that will advance our understanding of lunar science. Thank you.
Oh, great. Great, Mike. That's an amazing portfolio. It's really exciting. Mike Kynard, do you want to bring us home for this section?
Yes, sir. Glad to talk to you guys today, and I'm pleased to tell you about some of the activities that we have in the space nuclear propulsion world. Right here on the first chart, I think it's pretty obvious that we need a leap in performance over traditional chemical rockets that are now state-of-the-art to enable robust Mars transportation. And so NASA's actually looking at has a study going on, the Mars Transportation Architecture Study, that's looking at a couple of different nuclear options. The first is nuclear thermal propulsion. We've been looking at it for a good while. It was baselined back in the 1960s to go to Mars until NASA had a change in direction. It It provides high thrust, roughly twice, high thrust and also high performance. They're roughly twice what chemical rocket engines typically perform at. It does have short propulsion operation times, which allows it to be more robust. It provides also shorter trip times to Mars, and so that we can get our astronauts there safely and return when we need to, and also provides some robust abort capabilities. Allows us to be able to be reactive in case things we were to have issues. NASA's also looking at nuclear electric propulsion. Now that's really a game changer as far as not only going to Mars, but even going past there to explore the rest of the solar system. It has very, very high performance, roughly 5 to 6 times what chemical propulsion has as we know it today. And then it has obviously continuous access to electrical power because there's an electrical conversion system on it. And then for the Mars mission, it has the potential to be combined with a chemical stage to increase that thrust capability to allow our astronauts to get to Mars and back within a reasonable time. Next chart. We have several tech maturation needs for the nuclear thermal propulsion. The first one is we need high temperature nuclear fuels. Usually for terrestrial reactors and power reactors, the nuclear fuels are much lower temperature. We need fuels that react up in around the 3,000 Kelvin range, and then those require us to use refractory metals and or composites and things like that. And so it as part of our space nuclear propulsion effort that we have going on now. We have a fuel development program that has actually picked out a couple of candidate fuels. We're doing both nuclear and non-nuclear testing of those fuels, and we feel like we have a good path towards demonstrating those and proving out the performance that we would need to achieve the Mars missions. We also want to develop a low-enriched uranium reactor. Roughly a year ago, we moved away from adapting the rover Nerva reactors from the 1960s that relied on high enriched uranium, and we're moving more towards a moderator block design, and that design is can give us some advantages over a lower mass. We would use less uranium in that case, and we would be able to take care of some of the high power peaking issues that they saw in the rover Nerva days. We're hoping to engage industry on this very soon with an anticipated request for proposal to get some designs in for a subscale reactor and move forward from there. The third major thing that we would need from a technical maturation is cryogenic fluid management. I've often said that CFM is the holy grail of deep space travel, and it remains a focus in Space Technology Mission Directorate. And it's really more than just active cryo cooling. It's also all the passive things: low leakage valves, multi-layer insulation, mass gauging and settling, and things like that. A lot of great problems for ourselves and our industry to solve. Arthur Werkheiser, our friends at Glenn Research Center at Marshall Space Flight Center, as well as industry, are tackling this problem. They're actually tackling it for the human landing system, and we're hoping to be able to build upon that for our needs for nuclear thermal propulsion. Next chart. For nuclear electric propulsion, we have several subsystems that need to mature. Now, luckily, in many of these situations, we're going to be able to build upon some of the great work that's being done for the power propulsion element and for other things that are helping with their that are being developed for our human landing system. Now, for the reactor here, we're not trying to get very high heat as we would in the nuclear thermal propulsion world, but instead we're trying to generate electricity. Once that electricity has been made, we still have a lot of waste heat that we'll have to be able to dissipate, and with that we will need a method for doing that. So we're looking at liquid metal cooled reactor systems that are combined with our composite radiation heat rejection systems. All of that will need to be developed in a much larger scale than we've seen before from a radiator standpoint. We'll also need to convert that heat energy into power, and so we're looking at megawatt class power conversions. The MTAS study has baselined a Brayton cycle, and Brayton cycle has been looked at over several decades, and they've done a lot of work on bringing those up, but they're usually between 10 and 100 kilowatt systems, and we're going to need to be able to convert megawatt power. So we'll need to build upon that. One thing we are going to be able to take a great advantage of from the Gateway program is the work that's being done on the power and propulsion element in the area of high power electric thrusters. They're developing now about 12 kilowatt thrusters. There's work going on at the Glenn Research Center that pushes us up to around 50 kilowatt thrusters that have even been tested up to 100 kilowatts. We will need basically clusters of these 100 kilowatt thrusters to be able to perform the mission that's needed for the Mars transportation. I've already talked some about the cryogenic fluid management. We will need that also for our nuclear electric chemical hybrid propulsion. We need that for oxygen and methane and xenon in this case, which aren't quite as hard as the hydrogen. But again, I think Arthur Werkheiser and his team are going to be able to solve that for us, and got a lot of faith in him to be able to pull that off. The last thing would be in-space propellant transfer, and I think you will see a lot of that being developed under the HLS program, and also in conjunction with what Niki had talked about a little bit earlier with the in-situ resource considerations they're going to be doing at the moon. And I think that's all I have. Thank you.
All right, thank you. It's a great time for us to be pushing nuclear fission power and propulsion. So now what we'll do is I have a question that I'll start us off with that I'd like each of the panelists to kind of reply to, and as we wait for and look forward to some questions from the audience. And I'll tell you the order of, I want to mix up the order a little bit of who goes first. But my first question to each of you is to discuss your biggest challenge you see in advancing the technologies in your field for enabling moon to Mars space exploration. And Mike Seablom, I'll start with you.
Okay, I would probably say autonomous systems is the one area where we have been really pushing hard. We see that as an opportunity to really do great things, particularly in the outer solar system. We've talked about a mission to Europa to look for life. But on the moon and on Mars, these are areas where we can do a lot of science with better autonomous systems, with surface vehicles that are not necessarily controlled from the ground, but have science goal-oriented capabilities, can discover, be programmed for curiosity. And there's capabilities growing in this area, mostly in industry and academia, and I think we have to really take advantage of that. We had an autonomy workshop a couple of years ago, and it really opened our eyes to what the possibilities might be within 10 years. So the ability to exploit artificial intelligence and machine learning, the need to have onboard computing to support the autonomous systems. I think this is an area where we have opportunities to create more meaningful missions at the same or lower cost and lower risk as well. In terms of instruments, I think we've made strides in reducing power and mass in a lot of our science instruments. We have the possibility going forward using quantum sensors. We don't know what the full potential of those may be, but that could be a new area for us to get more precise measurements for the moon and for Mars and beyond. So I would say those are probably our key gaps, but there are opportunities as well.
Yeah, great. I like that answer. And certainly, I think it's also a place where the moon is a great proving ground as we go forward. Then, Mike Kynard, do you want to comment to this question?
Yeah, sure. I'm going to take a little bit different tact about it. Since our focus is nuclear technologies and moving forward with that, I think our biggest challenge is coming to grips with the regulatory issues and bringing a real case to the public on the actual risk and benefits of safely using nuclear energy for space exploration. I think that's the key to making this technology a reality. Also, I'm talking a lot more than just launching it in a decade or so. We need to be able to test these key technologies on the ground or in space a little later, even in this decade. And so we need good rationale. And I'm talking about a good story that we can tell. And we about safely tested nuclear technologies. We are using low enriched uranium. We have the National Space Policy Directive on space nuclear systems that can help us. We need good education to the public that says, hey, we think we have our act together and we think we can use this technology safely. My principal investigator, Mike Houts, keeps reminding me that as project manager, I'm likely to get the most radiation dose on the entire project just from flying back and forth across the country. And so we need to be able to tell that story and make people understand that, radiation is all around us and things like that. And if we want to move forward and be a spacefaring nation that really does exploration, nuclear energy is the key, and we need to be able to tell that story.
All right, thanks, Mike. That's a good area, and certainly critical for us. Jason, how about you?
Yeah, my first answer was going to be the confounding issue for us is going to be materials related, specifically the lunar regolith, which is incredibly aggressive, abrasive, very difficult to simulate on Earth. There's some great people working on it, Dr. Jennifer Edmondson, Dr. Doug Rickman, Dr. Kevin Cannon, Dr. Phil Metzger. So people are on it, but it's a really hard problem. And most organizations, companies, initiatives are going to work on like avoiding the lunar regolith, but we're going to have to build with it. So we have to actively handle it and mess around with it. And so the construction folks and the excavation folks really have our hands full with that. But what Mike said earlier about, or Mike Seablom said about needing space hardened and radiation hardened, like computing systems are going to be important for advanced robotics in space. And then of course, the regulatory issues are very true. I mean, especially sort of the political risk that because of the way we Americans fund our space program, perhaps innovative models like the way CERN funds itself, where there's just like a dedicated, you sort of lose the ability to advocate for more money, but you also take the risk off the table. And because this is going to have to be a long-term effort. And if we're always planning budgets on like 2 to 6 year horizons, it's going to be difficult to get there.
Yeah, thanks, Jason. And Niki.
Yes, hey there. Great answers from everyone. I would say that really within with consistent funding and access to the collaborative relationships we have, combined with our in-house efforts, I really believe we can meet our specific technology development goals and objectives. However, I do think it's key, particularly when looking at that mid-TRL development that I was talking about, which is where a lot of these technologies currently stand. You really have to start proving out the concepts and the processes as well to progress and take these from being a novel idea to a technology that really can be infused into a NASA mission or commercially. And that can be tricky. There's an art to it, which is why sometimes, especially that mid-TRL is kind of referred to as the valley of death. In order to mitigate that risk, you often have to test multiple approaches and processes in parallel with a focus on high risk and high benefit activities. So that's why we're very deliberate in when we're really designing or composing our overall portfolio for tech development to have a mix of our in-house and collaborative efforts. And I also think that all these challenges aren't technical. Assuming we do maintain those stable budgets and objectives, it's really critical that that we are able to not get married or too bogged down in groupthink, and that helps too when we do these challenges and partnerships. Not too married to a singular development path. We have to focus on being capability driven and not overly prescriptive when we put out solicitations and opportunities as well. Yeah, that's what I'd say.
Okay, great. Thanks, Niki. I understand we have a couple audience questions, but we'll let that build up a little bit and go to a second question from me and then go over to the audience. And so this second question, once again, I'll mix up the order of responders, but discuss what you see is an overarching trend or a critical next step to significantly advance? And Jason, I'll start with you.
Yeah, we've got to get to the moon. And I think everyone at NASA seems to be very focused on this, but we're only going to be able to mature these technologies so far in the lab and in Earth environments. And so I'm very excited to see all the enthusiasm for like getting onto planetary bodies, the moon, and then onto Mars, because I think that both as a proving and development ground, but as a just a maturation ground is going to be super important.
Thank you. Niki?
Yeah, sorry about that. Some problems with my mute button there. Yes, I'm going to follow up with that. My big one is we really ultimately need to have access to any place on the moon that we need. So when that is sustainable and when it's open to commercial providers, I think that is key. Also, I think if we through LSI can develop what I refer to as the pipes and roads for these capabilities, then we truly can reach sustainability and open up the commercial market on the moon, meet our national goals for successfully testing out these core capabilities that we also need to develop for Mars. This time we're going to the moon to stay, so we have to really establish that infrastructure to enable the sustainability. And a lot of that is being done through the commercial lunar payload services, having access to those early uncrewed flights to test out these demonstrations and work on establishing that infrastructure is really important. Mm-hmm.
Great. Thanks, Niki. Mike Kynard?
Yeah, as far as overarching trends, I think we're seeing a real spike in interest for space nuclear propulsion in the country. As you saw in my charts there, these are complex technologies that not only must be developed to work robustly, but in both cases, they also have to work together. And in some cases, I think the integration part of this job might be the hardest part of it. So the very complex problem that we're going to bring everybody's talent to bear. So we're already kind of taking that next step and harnessing all the interest from other government agencies and from industry. And so I'm real happy with the partnership we have with the Department of Energy right now. We seem to be working well with those guys to help us work on our fuel development plan and also our reactor development. We're hoping to get a industry involved very soon with our BAA. When we have that, we'll also be able to bring in the interest from our DARPA and SCO friends and Strategic Capabilities Office friends that where we can bring and align the things where we can do things together and make this more than just a NASA challenge, but also a nation challenge. And then, from that, the next step after that would be to get a really good mission pool once we have a handle on these technologies. And then this thing will be large enough and then everybody can have some fun.
Awesome. Thanks, Mike. And then Mike Seablom.
Yeah, I'd like to echo what I heard from Niki and from others about the infrastructure. I think that's really important. I think to put the infrastructure in place will then allow a commercial market to ensue. I don't think that's going to happen unless we do that. I see opportunities for science with human presence on the moon. There are things that we can't really do with autonomous vehicles today that humans can accomplish, and I think that'll be the case for another decade at least. So the best science can be done right now with humans on the surface, but having that infrastructure in place, I think, is critical for a commercial market to eventually flourish.
Okay, thanks, Mike. Now, Jim, do we have some questions from the audience that we can go to?
We do, sure. Let's give this one a shot. So this is for Jason. You were talking about the printing capabilities on the moon. So what are the next developments that you need to see, and what are the big challenges that you see in the shorter term to actually implementing this?
Yeah, so there's a lot of problems, as you can imagine, but the one that's sort of like, I would say the hardest, and the one that has the least kind of research to date done behind it, that'll need to be matured the most quickly, is what we refer to as the deposition subsystem. How are we going to manipulate the regolith to make it into a building material? I hinted earlier that like making concrete out of it's very hard because water sublimates on the moon. And so you're probably going to have some other manipulation method involving sintering or melting. And then so you can use resistive heating, you can use infrared, you can use lasers, you can use microwaves, but accelerating that research is going to be like that'll be like the key breakthrough that makes it possible.
Anybody else? Okay. And then I got one actually of my own for Mike Seablom. So we're about to, or pretty soon down the road, we're about to see a helicopter, hopefully successful on Mars, Ingenuity. What will you be looking for from that to think about autonomous vehicles, and will that alter the path that you might be going down as far as exploration of other of the moon, Mars, beyond, things like that?
I'm happy to say it. It's already changed the way we're doing science. Not only do we have a helicopter going to Mars, we have a helicopter going to Titan.
Right.
So we have 2 aerial vehicles that will be doing exploration, and we're going to learn a lot about the limitations and the capabilities of these aircraft. And yes, the autonomy is a big part of it, and we want to build more capable aircraft as we go forward. For Mars, this could be transformative in terms of how we explore the surface. Rather than crawling along centimeters per day, we can now perhaps do remote sensing and move from location to location very quickly. And so this, I think, is just the beginning, and we're very excited about those capabilities for places like Mars and Titan.
Yeah, and I'll add as a little bit of an aside that we're excited that helicopter really adds a great deal to the mission, and we're very happy to be part of the mission too. From a space tech standpoint, we've got 4 instruments on it ourselves. A couple of them which includes what we call terrain relative navigation to help us precisely land in more hazardous areas, so in much more interesting scientifically area, and also what we call MOXIE, which is our demonstration of producing oxygen out of the carbon out of the atmosphere of Mars. So it's a great mission and a great question, Jim.
So just to continue on that a little bit, since in a couple other sessions in here we talked about the rovers, the surface rovers being both autonomous and a platform to get astronauts around. Do we ever see the same for a helicopter or other aerial vehicle being autonomous, but also possibly carrying astronauts around?
That's not something we would do in SMD, so I'll hand that off to somebody else.
All right. Niki, did you want to take a cut at that, or do you want me to?
I don't think we have any plans for that at this time. It's an interesting proposition, though.
And what I would
folks on. Yeah.
What I would say is maybe what we can talk about is the sorts of things we are thinking about on the moon's surface. That would be autonomous behavior that we'd be modeling, and so it might be like we've got the large rovers, both from a robotic and a human exploration standpoint, but the sorts of things we're doing are things like hoppers and robotic scouts and stuff that would have a lot some of the flavor of that sort of thing. Do you want to talk about that a little bit, Niki? Absolutely.
Yeah, we have a lot going on there. As I mentioned earlier, especially when you think about the environment we're in and where we need access to. I think the news that just came out this week on where we think there may be more widespread water on the moon's surface and the type of areas we need access to, including permanently shadowed regions. So we have these little, what I'll call scouts, which autonomously driven little scouts that you can actually, I look at them a lot, possibly like a CubeSat platform that we use today, where you can actually crowdsource different designs, different instrumentation, different science and technologies that you want to test. So we actually just had a crowdsourcing competition for the first one we're going to fly. the little scout that JPL is helping to develop, where we said, okay, you know, if you have a payload, it's a little bit larger than for each scout, a little bit larger than a bar of soap. And what type of instruments might you equip these with, and the type of science and technology that you could do. So we have a lot going on in those areas. We had hundreds of entries across multiple countries. Mike Seablom was actually on that review panel, and so we're having a lot of discussion about how we could use those. Also, just how we're developing autonomy and how these things can not only work independently and individually, but how they work as a kind of ecosystem or a cluster together. They can do that as well. Is an interesting prospect that we're exploring and working with our autonomous systems developers in. And so I think someone mentioned early in the discussion today how important it is to involve universities and industry in this development. There's a lot going on here on the ground in these areas that we can leverage and create as well. So I think all of those things could flow into the further down the road kind of question you were asking, Jim, on how we might be able to use that. But the autonomous systems and the commonality between those would probably still be very key. And Mike Seablom, I don't know if you wanted to add anything to that.
No, I agree. And with industry, you know, with autonomy, what I was saying earlier, NASA's not going to be the leader there. We're not going to, I mean, with the commercial market for autonomous vehicles, we're going to have to leverage what they're doing, and that's key. And in academia, places like Carnegie Mellon, they're doing phenomenal work. Even Google. So I think we have to be aware of what's going on, and we have to be prepared to work with our partners.
And just to pull on that thread, it goes back to what I mentioned earlier about you're exactly right, Mike, that NASA is not going to be the lead there, which is why it's so important that we are capability focused. What are the capabilities we need? And when we're not overly prescriptive in requirements, when we put out these types of opportunities, we get the most diverse and creative and innovative approaches that, quite frankly, we haven't thought of in-house. Any large organization is capable of groupthink. So, for example, one of the tipping points we just awarded was to Intuitive Machines for a deployable hopper that would be ready in late 2022 to fly. We also just awarded Intuitive Machines as well for Eclipse, the commercial lunar payload services I mentioned, to deliver the first drill and mass spectrometer to look for water on the moon. And so we have a lot going on in this area that we're already starting to leverage in addition to the small rovers that I mentioned.
Okay, thanks. That was a great answer. Jim, do you have a couple more questions for us?
Yeah, I think so. We had a question very early on about, let's see, RTG technology and nuclear fission reactors. How essential is that technology to a sustainable, effort here? Is there significant progress that we're seeing right now, or are there just some hurdles that are just going to make it take a long time?
I can see a few people potentially answering that. Niki, do you want to talk about it from an architecture standpoint? Mike, I don't know if you want to talk about it from a science perspective, especially with RTGs, and then Mike Seablom and Mike Kynard maybe also. So, Niki, do you have some thoughts, or do you want us to go on? Oh, you might be muted.
Looks like our audio might have gone out.
Audio may have just gone. Mike Seablom, do you want to comment? Or we'll turn it over to Mike Kynard.
Yeah, it's clearly an area where we use these for all of our deep space missions, and we're investing in development of new capabilities all the time. So I think we've got enough for what we need for the science aspect. For human exploration, I'm not sure what you need beyond what's being developed now.
And yeah, I'll comment too that, if we're going to truly, before I turn it over to Mike Kynard to see what he wants to add, would be in order for us to truly explore all of the moon as we go forward and really operate in a sustainable manner. One of the things we need is to not be reliant on the sun for all of our power. And so in that application, things like a fission surface power for a little bit more power than we can get out of an RTG is something that has a continuous supply, is something that's high on our priority list. And also all the RTGs make a great instrument, just as they've shown throughout through a lot of the science missions. They make a great local heater and electric power provider for an instrument to survive through the lunar night and through the very cold temperatures. The moon is one of the coldest places on the universe when it's at certain times in certain places. Mike Kynard, do you have anything you want to add?
You covered it very well. The only thing I would add is that we really need our fission surface power friends to be successful, because we plan to build on that technology as they plow the road for us, especially for nuclear electric propulsion, because when they become successful, then we can move forward from there. But I agree with you. We have to have fission surface power be successful for an economy on the moon. We just simply have to have that kind of power for in situ resource and the other things that we will need to do once we get there.
If I could
Yeah,
just
can y'all
jump
hear me?
in real quick.
Yes, we can, Niki. Mike, Seablom, make your comment, and then we'll turn it over to you, Niki. Great that you're back.
Yeah, I'm sorry. So I want to get back to the need for infrastructure, right? I mean, what are the long-term implications of having a lot of nuclear batteries on the moon over a period of time? If you're thinking long-term, sustained human presence, as opposed to an infrastructure that would be more controlled and perhaps cleaner. I don't know. I would like to hear some thoughts on that.
And Niki, do you want to?
Can y'all hear me okay?
Yep,
I had to
sure.
disconnect. Okay, it was the AirPods then. Sorry about that. Yeah, so I agree with everything that's been said, and we can definitely go back and revisit what Mike Seablom was asking, but I did want to state that obviously power is key. We're very interdependent in all of these things, as I talked about with LSII, but power is one of the areas that's the most critical that we worry about early on, from establishing an infrastructure and having a phased roadmap and development plan and understanding the real architecture need and pull. It's obviously also something that our commercial and international partners need. We all need equally, which is why it's one of our key focus areas for the consortium that I mentioned earlier. As a matter of fact, the fall meeting we just had 2 weeks ago, we made power the key theme for that whole meeting. And so we had 9 different breakout sessions throughout the 2 days, where for each of the capability areas, we talked about power, what the power needs were, the kind of chicken and egg of how you get there. And like Jim Reuter said, it's going to require really a suite of capabilities and technologies. And that's why I wanted to mention, we do have an RFP that's on the streets now for solar array technologies. And then Mike Kynard, I was going to ask him to also talk a little bit about the RFP or RFI, I think, that might be out now for the surface fission power and kind of the timeline. I want to make sure that we amplify these opportunities and get the word out, because we are very codependent in developing the capabilities and technologies that we're going to need to establish that infrastructure.
Jim, I might say a word here about this as well, because we have looked at it at ICON as we like to design the system. Power inputs are a big consideration. And with anything except nuclear, you're really just like sipping power, and it impacts the rate of construction and how hard you can push the robotics and autonomous systems. And when you really consider it from like a power to mass ratio, there really is no competing with nuclear. The mass of batteries you would need to survive a 14 Earth day lunar night, your whole program would be flying batteries to the moon. Nuclear is I would think it's certainly essential.
Yeah, thanks, Jason. Hey, what level of power for surface power would you say that you would need from your perspective?
I would love to have 2 kilowatts. We will see if I can have that. Again, probably not without nuclear, but it really does transform how fast we get to build the moon base.
I actually asked because, depending on the scale and what you're dealing with, people talk in terms of tens of kilowatts or more. And so I was just curious if for your particular case, 2 kilowatts is at least in the ballpark.
It is. Okay. That's right. I mean, if you can give me 10, I'll do 10. But our machines right now, our base, where we have like unlimited power, 2 kilowatts is sufficient for our terrestrial operations.
Excellent. Thanks.
And just to answer Niki's question, I think it's right after the first of the year when we plan to put out the RFP for the fission surface power. And so we'll be looking for good solutions there. And I think that system's up to 10 kilowatts. So we'll be able to take care of Icon's needs.
Yeah, and I wanted to note too from that fall meeting I just mentioned, we're going to be publishing all the results on the LSIC website that Johns Hopkins APL leads. And so they're just like the conversation that Jim Reuter and Jason were just having about who needs what and how much you would need early on. We had a lot of those discussions with a lot of potential users. And so we've captured a lot of that and we'll be publishing that publicly.
Okay, great. Let's see, I'll go a little bit quickly to our third question. So because we only have about 5 minutes left. So could each of you share a possible avenue for industry engagement to help contribute to advancing the needed technologies in your field? And I'll start with Jason. Oh, I'm sorry, Mike Kynard. Sorry.
Yeah, well, we've talked about some early engagement. We hope to have a broad area announcement or RFP out very, very soon, hopefully in the November timeframe for a subscale nuclear reactor for our nuclear thermal propulsion efforts. Fission surface is coming up at the beginning of the year. We're hoping to have that out the door. I think we need to take care or take advantage of BAAs, Space Act agreements, and interagency agreements, actually, so that we can use other agencies and their procurement power to reach out to industry and do things as well. I did like, and something that really spoke to me was something that Niki said earlier, and that's that we've got to get smaller, innovative companies in collaboration with some of our more traditional, longtime industry partners, and so that the innovative guys can take advantage of the lessons learned that some of our more proven partners have, but we could get away from maybe some of the groupthink that Niki was talking about a little earlier.
Okay, great. Mike Seablom?
Well, I think it's an extension of what we're already doing through small business innovative research and our regular solicitations. And that is, the continued miniaturization of the science instruments, the low swap capabilities. We want to put them in small spacecraft. We want to be able to do more science for less money. And then for the surface vehicles, like I said earlier, I think the autonomous capabilities will deliver much better science. And I think that's critical for Mars. It's critical for exploring the outer solar system. So, I mean, just continued investment in industry in those areas, I think, would be of great benefit to us.
Okay, thanks. Jason?
Yeah, I don't have ideas for new ones other than say like Icon's maybe a poster child for how this happened, right? We participated in the Centennial Challenge, which cost NASA sort of next to nothing, a rounding error, to look at 20 different ideas. They then found at least one partner and maybe several partners in Icon and others. Now they're taking like a partnership kind of bet with the Department of Defense and the Air Force, and Icon had to put up some serious money too to participate. So we all shared the risk. And then if they like what they see. And so I think the way NASA has thrown open the doors of late to public-private partnership has been, at least from Icon's perspective, it's working.
Great. And Niki, you want to round this question out? Then we'll hopefully get one more question from the audience.
Sure. Yeah. Well, obviously, I feel passionately about this. I think we have to use the broad spectrum that we have. I think they're pulling up a chart now. I just wanted to briefly show for space tech, these are opportunities that we have every year throughout the year. You can see in green the ones we have open now. We are, I will say, more than assertively, we're aggressively pursuing these types of innovative and novel partnerships and collaborations, because this is what it's going to require to get sustainability on the moon. So that's why we have the consortium. It's why we have these opportunities. I really encourage folks to go take a look on the website we have there, and we're really trying to amplify this and get the word out on all the opportunities we do have. That's it.
Okay, thanks. Jim, one last question from the audience?
Yeah, one last question. It's pretty simple, yes or no, really. This comes from our sponsor, actually. Is space-based solar power beamed from lunar orbit an option for clean energy on the lunar surface?
Niki, did you want to try that? Yes or no?
Well, I'll just say it's one of the options, and I would encourage folks to go look. We have the vertical solar array technologies RFP that's on the streets right now, and so we're open to a suite of potential capabilities.
Okay, Jim, do we have time for a lightning round question? I just want to ask each of the panelists here right at the end.
One
And
sentence each, go.
Yeah, one sentence each. What keeps you up at night? And it can't be kids or dogs. Niki?
Consistent funding.
All right, Mike Seablom.
Yeah, I agree. I think that the way I hope we don't get whiplash from this, if you know what I mean. It would be nice to have sustained investment in one area for a long time.
Okay, and Mike Kynard?
They stole my answer. Consistent funding, right? We need to be on a path and be able to make consistent progress.
Thanks. And Jason, you get to round us out.
Moon dust.
Moon dust. Great. All right, Jim. I think we've come to the completion here. I really want to thank all the panelists for really a great answers and responses, and Jim for hosting us here. Thanks.
Hey, thank you to everybody. Really appreciate it. It was a great session. It was very cool, and we'll start the GoFundMe for the all the funding now. See if we can get that done. All right. Thank you so much.